Hi, everybody. Welcome back. This is lecture 6, and today we're going to be talking about a descriptive statistic calculation called the z-score. And we're going to go back to actually, I think this is a new example. We've not seen this before. Forced vital capacity. Forced vital capacity in respiratory therapy is the amount of air a person can exhale after taking a deep breath. So imagine exhaling and taking a deep and trying to exhale out. This is a measure that's used to assess lung function, particularly in patients with conditions like asthma, chronic obstructive pulmonary disease, and other pulmonary issues. So forced vital capacity, a person will expel more air in a better situation, and if they could expel less air, it's more at a disadvantage. The person is more at a disadvantage. So forced vital capacity in healthy adults tends to follow a normal distribution. And last lecture we did discuss that normal means bell-shaped and symmetrical. And we're told here the population mean forced vital capacity is 4.5 liters, and the population standard deviation, sigma, is 0.5 liters. So we're not being asked to compute either of these values. They are being provided to us in this problem. Label a bell curve with forced vital capacity values from 3 standard deviations below the mean to 3 standard deviations above the mean. And this is a repeat of what we did last class when we introduced the empirical rule. So let's start. We're going to do this in a second. Let me give you the question, and then we're going to come back to the picture and answer the questions. So using, we're going to graph out the 3 standard deviations below to 3 standard deviations above, and then we're going to answer these questions. What percentage of healthy adults have FVC measures between, and we're going to do each of these. 4 to 5 liters, 3.5 to 5.5 liters, 3.5 to 4 liters, 4.5 to 5 liters, 3 to 4 liters. And how would you assess a patient with an FVC measure of 5.7 liters? So let's go back and remember that, and also how would you assess a patient with an FVC measure of 3.1, and that's liters. So let's remember what was provided to us before we started looking at the question. We were given the mean and standard deviation, and that's the way we're going to be able to answer these questions. So given the mean and standard deviation of 4.5 liters is the mean and a standard deviation of 0.5, we can label one standard deviation above the mean by we're adding a standard deviation to the mean, and that's where we get the 5.0 from. So in this problem, the standard deviation is 0.5 liters. So what we're doing is adding that standard deviation to 4.5 to get 5.0. That is one standard deviation above the mean. And we do that again. We add another standard deviation. We get 5.5. So from 4.5 plus a half is 5, plus another half is 5.5. And we'll do it one more time on the right, plus another half, another standard deviation, 6.0. Now, the standard deviation is not always 0.5. It is in this example. So in different examples, we would be adding different values, not necessarily 0.5 each time. Let's look at the left side of the bell curve where we start in the center with 4.5, but now let's subtract a standard deviation. So subtracting minus 0.5 gives us 4.0, minus 0.5 again gives us 3.5, and minus 0.5 again gives us 3.0. Okay. So by the definition of the empirical rule, we know that 68% of the population falls between one standard deviation below to one standard deviation above. Okay, so I'll shade in that area. One below to one above. This is 68%. And cutting that 68% in half, this is 34 and 34%. And then the empirical rule went on to say that if we look between two standard deviations below to two standard deviations above, the total was 95%. And through some subtraction, we were able to figure out that that meant this was 13.5%, this piece right here, and this other piece on the other side, 13.5%. And if we add up, and if you have trouble understanding where these numbers are coming from, go back to the last lecture on the empirical rule. If we add these numbers up, the ones that I'm boxing in, we'll get 95%. Okay, and the last piece was, okay, and hold on. So here are the answers to the next parts of the question. The question said, what percentage are we going to see between 3.5 and 4 liters? So if we look at that on the graph, here's 3.5, here's 4, and the answer between those 2 points is 13.5. And between 4.5 and 5, that's between here and here. And on our graph, we see that that's 34%. And between 3 down here and 4 up here, okay, again, we're going to apply the empirical rule to this. And the empirical rule said that 99.7% were within 3 standard deviations, 3 below to 3 above, 99.7. So using subtraction and division, we figured out that that meant 2.35% on the left and 2.35% on the right in this piece, in this segment right here. So in order to figure out 3 to 4, we have to take that 2.35 plus 13.5, and that's going to get us from 3 to 4. Okay, so 2.35 and 13.5 gives us 15.85, and that would be the answer to 3 to 4 liters. Okay, so sometimes we can really get enveloped in the math and in adding and subtracting and forget about what we're actually looking at. But let's remind ourselves that the empirical rule gives us a snapshot of what a normal distribution is looks like. We see that most of our data is in the center, and we see that less people fall on the far left and less people fall on the far right. Okay, so now taking that example a little bit further, how would we assess a patient with an FVC measure of 5.7 liters? Because if we go back to our picture, which I know looks a little messy here, 5.7 isn't, or is it 5.7 or 4? It's 5.7 is not on our horizontal axis. We have 4.5, we have 5, we have 5.5 and 6, but we don't have 5.7. We know it's somewhere in here, but we don't yet know, we don't have a percentage. We don't know details like that. But because we see it up here between 5.5 and 6, we know that it's probably a relatively rare FVC. So we would say that because it's between 2 and 3 standard deviations above the mean, it is rare and it reflects exceptional lung health. Okay, exceptional because it's on the right-hand side. It may be seen in an athlete or a person who engages in regular cardiovascular exercise. So that's what we see up on the right-hand side. These are exceptional FVC measures. And let's look at an FVC measure of 3.1. So going back to our picture, where is 3.1? Well, okay, here's 3, and here's 3.5, so 3.1 is somewhere within this range. So we see this being on the far left side of the curve. So between 3 and 3.5, 3.1 liters is between 2 and 3 standard deviations, but on the left side, below the mean. So we're looking at this area down here. This patient is at risk of having restrictive lung diseases. Respiratory therapy interventions such as breathing exercises or bronchodilators may be necessary. So these are exceptional, and good. And down here, these measures are poor and need some extra help. Okay, so let's now talk about what a z-score is. A z-score is a numerical measurement that describes a value's relationship to the mean of a group of values. So it's relationship to the mean. A value's relationship to the mean. It tells you how many standard deviations a data value is from the mean. So if we take a look at these red numbers beneath the liter measurements, we see that in the very center, the value 4.5, which is the mean, has a z-score of 0. So 4.5 is the mean, it has a z-score of 0. 5.0 is 1 standard deviation above the mean. And so we say that the z-score for 5.0 is 1 because 5.0 is 1 standard deviation above the mean. This tells us how many standard deviations a data is from the mean. So 5 is 1 standard deviation from the mean. 5.5 is 2 standard deviations from the mean. 6.0 is 3 standard deviations from the mean. Now these are positive numbers, positive 1, positive 2, positive 3, and so these are numbers that are on the right side of the mean, above the mean. On the other side, we have values that are below the mean. So let's take a look on the left side. 4.0 is 1 standard deviation below the mean. So we subtract the standard deviation to get 4.0. That has a z-score of -1. It is 1 standard deviation below the mean. 3.5 has a standard deviation, or we subtracted 2 standard deviations to get to 3.5, and so its z-score is -2. 3.5 is 2 standard deviations below the mean. And 3 is 3 standard deviations below the mean. Okay, so we subtract the standard deviation 3 times to get that number. So if a z-score is positive, like we see on the right-hand side here, it means that the forced vital capacity is above the mean. So the mean, 4.5, look at these numbers, 5, 5.5, and 6 are all above the mean. They have positive z-scores. Z-scores that are negative are below the mean, values that are below the mean. So if the mean is 4.5, 4.0, 3.5, and 3.3 are all values that are below the mean. And so their z-scores are negative. The z-score of 0 has an important place. It's right in the center of the distribution because a z-score of 0 is the mean. This is the forced vital capacity that is the mean, 4.5. For the population of forced vital capacity values, higher z-scores represent better lung capacity, better lung function, more air is exhaled, while lower z-scores could indicate possible respiratory issues. So that's what we're looking at up here. These are the high z-scores, better lung capacity, versus down here with lower z-scores and potential respiratory issues. So before I move on to the formula, I want to take this example and expand it to other ideas because forced vital capacity is just one of many variables that are normally distributed. So if you are told that a variable is normally distributed in any application, so it could be in healthcare or business or education, but if you're told that something is normally distributed, then the bell curve, the normal distribution, can be labeled in this manner with 1, 2, 3 standard deviations above the mean, measuring z-scores of 1, 2, and 3, or on the left side, 3 standard deviations below the mean with z-scores of -1, -2, and -3. What changes from problem to problem are these values because the variable is different from problem to problem, but the z-scores do not change. They are always 1, 2, 3 on the right and -1, -2, -3 on the left. So the z-score has a formula because going back to this picture here, we have a z-score of 0 in the center and a z-score of 1 just to the right of that, but there are lots of z-scores in between 0 and 1, and they are valid z-scores as well. So we're going to use the formula to calculate those valid z-scores that could exist anywhere on the horizontal axis. Okay, and most of the time, it turns out 99.7% of the time, a z-score is going to be somewhere between -3 and +3, 99.7% of the time. In exceptional cases, we may get a z-score that is more than +3 or less than -3, but that happens 0.3% of the time. It's a very rare occurrence. So let's figure out how to calculate a z-score that's not a whole number, something that could be in between these whole number z-scores. And so we use the z-score formula. You can apply the z-score formula for any normal distribution, but you have to be provided with the mean and the standard deviation for that distribution. And this is the general formula. The symbol that we use for the z-score is just a z, and it's a z either for the population or the sample. We use the same symbol. We take the data value in the distribution, we subtract the mean, and divide by the standard deviation. So putting this into symbols for a sample and a population, let's look. In the sample, we have z equals, the data value is x, the sample mean is x bar, and the standard deviation is lowercase s. Okay, and for a population, we have the data value is x, the mean is mu, and the standard deviation is sigma. X minus mu over sigma. So in both cases, z is the variable, z is the letter that we use, the symbol to represent the z-score. The data value in both cases is represented by x, and the mean is represented by either x bar or mu. And in the denominator, the standard deviation is represented by s or sigma. Okay. So it's important if we do this on the calculator, it's important to recognize the numerator must be wrapped in parentheses if we do this in one step, because if we don't, we end up dividing first, and we don't want to do that. So let's look at an example. Let's use the forced vital capacity example, and we are being provided with the mean of this population, and I know it's population because I have the mu symbol, not X bar. And I'm told that the mean is 4.5 liters, and I'm told that the standard deviation is 0.5 liters. Okay, let's find for a patient with a forced vital capacity of 4.9 liters, let's find and interpret the patient's z-score. So let's realize what this problem provides us with. Mu is 4.5, sigma is 0.5 or 0.5, and the x, the data value for this particular patient is 4.9. So different patients are going to have different X's, different data values, and we'll be able to find z-scores for many different patients. But when we calculate a single z-score, it's for one member of the population. So we're going to find it through this formula, and then we're going to interpret it. So here's the formula, and we're going to plug in the data value X is 4.9, mu is 4.5, and sigma is 0.5. Okay, so 4.9 minus 4.5 divided by 0.5, and we get 0.8. Now, if you want to see me do that on the calculator, just give me a moment. I'll show you the difference between using parentheses and failing to use parentheses, because that could really change your answer and make it incorrect. Okay, so here we are. Let's use parentheses. 4.9 minus 4.5, parentheses, divide by 0.5. Okay, and 0.8 is our z-score. So this is an example of how a z-score is not necessarily a number, an integer 0, 1, 2, 3, or -1, -2, -3. A z-score can be a decimal anywhere on that horizontal axis between two graphed z-scores. Now, what happens if I forget the parentheses? Then what happens is the 4.5 is then divided by 0.5 first, and then the subtraction occurs, and that gives us a way different answer. Okay, and this is incorrect. So let's make sure that when we use z-scores, we wrap the numerator in parentheses. Okay, so our z-score here is 0.8, and let's give that person an assessment. So 0.8 is above average. It's a positive z-score. So it means that this patient's forced vital capacity is 0.8 standard deviations above the mean. The patient has slightly above average lung function. So let's remember what that looks like visually. The mean was 4.5. One standard deviation above was 5.0. This patient is not quite as high as 5.0. This patient is 4.5, 4.9, 4.9, and the z-score for this patient is 0.8, 0.8. So here we have a z-score of 0. Here we have a z-score of 1. This patient right here has a z-score of 0.8. And it is above average. It's on the right side of average, the right side of the mean. So it's above average forced vital capacity. Okay, let's look at example number 2. With the same mean and standard deviation, let's find the z-score for a patient with an FVC of 3.7 liters. Let's interpret that patient's z-score. So using X, the data value, this time as 3.7, we're going to stick with the same mean of 4.5 and the same standard deviation of 0.5, but we're plugging in an X of 3.7. So using the z-score formula again, plugging in 3.7 for X minus 4.5, wrap that in parentheses and divide it by 0.5. And we're going to get an answer of negative 1.6. Okay, I'll show you on the calculator doing this. So we have 3.7, the patient's forced vital capacity, minus the mean, 4.5. Close the parentheses and divide by the standard deviation 0.5. Now, before we even get an answer, 3.7 is below the mean. So we expect a negative z-score to come out of this calculation because the person's forced vital capacity is on the left side of the mean, the left side of the center of the distribution. So we expect a negative z-score, and if we don't, we would want to come back and check our work. But looking at this, we have a z-score of negative 1.6, which is not great. So we should go back and interpret that forced vital capacity, knowing that it's between 2 and 3 standard deviations below the mean. Okay, so with a negative 1.6 z-score, the person's forced vital capacity is 1.6 standard deviations below the mean. So here is our bell curve again, our normal distribution with the mean in the center at 4.5. And this patient, not 1 standard deviation below the mean, and not quite 2 standard deviations below the mean, 1.6 standard deviations below the mean. Negative 1.6 means you're 1 and 0.6 standard deviations below the mean. So this is a patient with likely reduced lung function, and further investigation or respiratory therapy might be needed. So we've got somebody on the low end. So you could see the big difference between a person over here and a person that's way up here. Visually, it makes more sense when you graph it on the distribution. Let's look at a third example. In the same application with 4.5 as the mean and 0.5 as the standard deviation, let's look at a patient with a forced vital capacity of 6 liters. And this person comes in for an evaluation. Let's find and interpret the patient's z-score. So now the data value is 6. We're going to plug in 6 for x. So parentheses 6.0 minus 4.5 divided by 0.5, and our z-score is 3.0. So this is exactly 3 standard deviations above the mean. The z-score of 3.0 means that the patient's forced vital capacity is 3 standard deviations above the mean, and that's exceptionally high lung capacity, potentially indicative of an athlete or someone with superior lung function. Okay? Because anything higher than that is going to occur 0.3% of the time. So here's the mean, here's 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. It's a very rare occurrence to be that high. Okay, so some takeaways you want to make sure you understand with z-scores. They help us quantify how far a patient's FVC is from the average lung capacity, making it easier to determine if their lung function is typical or needs intervention. A positive z-score always indicates above average lung function. A negative z-score always indicates below average function. And in respiratory therapy, understanding a patient's z-score can guide clinical decisions about interventions and treatment plans. So the z-score takeaway for forced vital capacity is very similar to the z-score takeaway for any distribution, because z-scores give us that information about how far a value lies away from the mean. The mean is a z-score of 0. The z-score calculation of a data value tells us if we are far away or close, and if we are on the left or the right. Positive numbers will be on the right, negative numbers will be on the left, and values that are much greater than 0 are going to be on the far right, and much less than 0 or on the far left. Okay, so let's try this one. If you like, you can pause the video and try this on your own or just follow along with me. We're going to change the variable from forced vital capacity to gait speed, and we did an example with gait speed at the last lecture. The gait speed for this should say healthy older adults is normally distributed. So we're told that we're dealing with the normal distribution, and the mean is 1.2 meters per second. The standard deviation is 0.2 meters per second. So we have to be provided with those two pieces of information to do the z-score formula. We're going to find z-scores and interpret z-scores for gait speeds of 1.5 meters per second, 0.9 meters per second, 0.6 meters per second, and match the classification below to each z-score. Severely reduced mobility requiring immediate intervention, or reduced mobility and at a higher risk for falls, or excellent mobility. So we can determine which one of these fits each of these and match them. So let's recognize that z-scores are going to be positive for gait speeds that are above the mean, and z-scores will be negative for gait speeds that are below the mean. And if we're given the mean of 1.2, we already have an idea of the kinds of z-scores that are going to come out of these calculations. 1.5 being more than 1.2 is going to be a positive z-score. 0.9 is less than 1.2, so that will be a negative z-score. And 0.6 is less than 1.2, and that will be a negative z-score. So let's apply the formula 3 times. Each time the x changes, but for each of those calculations, the mean is still going to be 1.2, and the standard deviation is going to be 0.2. So here's the formula. Okay, so for 1.5, when x is 1.5, let's plug in 1.5 minus the mean 1.2 divided by the standard deviation 0.2. And we do that, we get 1.5. So that's a big coincidence, and don't expect that to happen too often, where the data value is the same as the z-score that comes out. That often does not happen, but it happened here. So what it means is that this patient's gait speed is 1.5 standard deviations above the mean, which is a good gait speed to be higher than average, more than 1 standard deviation above, some halfway between 1 and 2 standard deviations above the mean. Okay, let's do, I'm sorry, this is a mistake. This should say 0.9. So for 0.9 meters per second, let's plug in 0.9 for x. Again, we're using the mean of 1.2 and a standard deviation of 0.2. And this time we get a z-score that is negative 1.5. Negative 1.5. So we're going to say that this patient's gait speed is 1.5 standard deviations below the mean. Below, because it's on the left-hand side, it's negative. And above, because it's on the right-hand side, it's positive. And okay, one more, and I mistyped this one too. This should say 0.6. So for the last patient with a gait speed of 0.6, plugging in that 0.6 where x is, subtract the mean and divide by a standard deviation. This one gives us a z-score of negative 3.0. So because it's negative, it is below the mean. This patient's gait speed is 3 standard deviations below the mean. Okay, so we're going to classify that as severely reduced mobility, requiring immediate intervention. That is the worst of the 3 z-scores that we have. So this is 1.5, negative 1.5, and negative 3.0. And this one is the worst. Okay, the next worst is the negative 1.5. And so this is, we could say, between our 3 z-scores, this one is in the middle. This person has reduced mobility and at a higher risk for falls, but not as bad as the negative 3.0. And then the last one with 1.5 is excellent mobility. Okay, so we were asked to match the gait speeds to those 3 classifications, and based on the values that we got, this is how we would classify them. So understanding z-scores recap, let's remember what a z-score is. It's a numerical measurement that describes a value's relationship to the mean of a group of values. It tells you how many standard deviations a data value is from the mean. And here's the formula, either for a sample or for a population. Notice that the formula is the same except for the symbols being used. We abbreviate the z-score symbolically just with the letter z. Most of the time, z-scores are going to range from -3 to +3. So if we calculate the z-score for a patient's gait speed, we're going to see a number likely between -3 and +3. If we calculate a z-score for a person's forced vital capacity, we'll likely see a z-score between -3 and +3. For cholesterol, for blood pressure, for height, weight, most variables are going to be somewhere between -3 to +3. But sometimes we do have values outside of that range. Those are the outliers, and they do occur, but they occur less than 0.3% of the time. Because remember, the empirical rule told us that 99.7% of all of our values fall from 3 standard deviations below to 3 standard deviations above. When assessing z-scores, you must consider the variable that is being measured. For example, an ideal z-score for bad cholesterol is low. So you like low z-scores when you're dealing with cholesterols because low cholesterols are better. But for lung capacity, let's change the variable for lung capacity. If we measure a z-score for lung capacity, we want something on the high end. 2.7 would be more advantageous because high values are better in lung capacity. So it depends on the variable that's being measured. Sometimes you'll want, it's better to have a z-score that is low, and sometimes it's better to have a z-score that is high. So let's look at examples where we compare 2 z-scores. A nurse is evaluating 2 patients based on their systolic blood pressure improvement after treatment for hypertension. The goal is to determine which patient had a better improvement. Okay, so we have a group of patients that were treated with, this is a made-up drug, hypertrova, and the average reduction, or the average reduction or the average improvement was 12 with standard deviation of 3, and patient 1 improved by 14 after treatment with hypertrova. Okay, so this means the improvement in blood pressure, which is actually a reduction in blood pressure. So then there's another made-up drug, Preceval. The average systolic blood pressure improvement was 8 mmHg. So we have a difference in the average decrease. The standard deviation was 1.5. Again, we have any problem that we have to do with z-scores, we have to be provided with both the mean and standard deviation. And this patient improved by 10 mmHg after treatment with this drug, Perceval. Okay, so we're going to determine the z-score for both patients. And we're going to, sometimes when z-scores don't come out to terminate, if they don't terminate, we are going to round them to 2 decimal places. And we're going to decide which patient had the better improvement relative to its own distribution. So patient 1 and patient 2 each are going to have their own z-score. Let's calculate patient 1 first. They had a data value of 14, the mean is 12, and the standard deviation is 3. Okay, so the person, where is it? Person improved by 14 mmHg. This is the x part of the equation. The average, the mu part of the equation is 12, and the standard deviation part of the equation is 3. So let's find the z-score for an x of 14. Plugging in to the z-score formula, we have x minus the mean divided by the standard deviation. So we're going to be taking 14 minus 12 divided by 3. Now this turns out to be 0.666 repeating, and we're going to round this to 0.67. Okay, so when the decimal does not terminate, we're going to round to 2 decimal places, 0.67. Let me show you on the calculator what it looks like when the decimal doesn't terminate, when the number doesn't terminate, sorry. Okay, so 14 minus 12 divided by 3. Okay, so this is what it looks like when it doesn't terminate and we need to round this number. So we're going to look at rounding it to 2 decimal places. And when we look at the 0.66 and we see that the next digit is another 6, we're going to bump this up to 0.67. So the z-score here is 0.67. Okay, so that's where the 0.67 comes from, and let's interpret this. The z-score for patient 1 is 0.67. It means their systolic blood pressure improvement is 0.67 standard deviations above the mean. Okay, so when z equals 0.67, the improvement is 0.67 standard deviations above the mean. So let's visualize what that could look like. The mean, 1 standard deviation above is over here, and this patient falls maybe right around there. So this is patient number 1, sorry. Okay, done. And sorry. Okay, so that's what patient number 1 evaluates to. Let's look at patient number 2 now. Same mean, I'm sorry, no, there's a different mean, different standard deviation because they were in a different group of people, a different drug. So this drug, Perceval, had a different average, 8 mmHg, and a different standard deviation, 1.5. So now let's calculate this person's z-score. This patient, I think it's patient 2 here, improved by 10 mmHg. So let's find the z-score for this patient. So let's plug in 10 for x, the mean is 8, and the standard deviation is 1.5. Okay, so 10 minus 8 divided by 1.5. And this also requires us to round on the calculator. We're going to get 1.33. And let me show you what that looks like on the calculator. So we're going to take parentheses 10 minus 8 divided by 1.5. Okay, this also doesn't terminate. And now when we take this 2 decimal places past the decimal point, we see 3, 3, and the next number is 3. It's not 5 or greater, so we're going to keep this value as 1.33. So this person's z-score is 1.33, which is pretty good compared to the other one. Okay, so that's where the 1.33 comes from. And so to interpret this patient's z-score, this is patient 2 with a 1.33 z-score. It means their improvement is 1.33 standard deviations above the mean. So here's the picture, 1.33. So now if we do a comparison between the two of them, where patient 1 was 0.67 above the mean, sorry, this keeps adjusting. Okay, patient 1 was 1.6 was 0.67 above the mean, and patient 2 is 1.33 above the mean. When we do the comparison, we see that patient 2 has the better improvement relative to the group that they took that drug. So Pressivol, the patient with Pressivol has the more improvement in their group. So this is how we're going to answer this. Which patient's improvement is better relative to their group's distribution? Do we have patient 1 in the Hypotrova distribution or patient 2 in the Pressivol distribution? Let's remember the z-scores. 0.67 was the improvement for patient 1, and patient 2 was 1.33. So patient 2 has the better improvement relative to its distribution. Patient 2 has the higher z-score, meaning that their improvement with Pressivol stands out more compared to their group, even though the improvement 10 mmHg is lower than patient 1 improvement of 14 mmHg with Hypertrova. So we have when we compare the numbers 10 and 14, we do have a difference in improvement, but that's not what this question is asking us. It's asking us to look at our z-scores and determine which patient's improvement is better relative to their group's distribution. So you're not looking at patient compared to the other patient. You're looking at how did the patient fare relative to the rest of the patients in their group. And that's how we answer this question, by comparing z-scores and choosing the higher of the two z-scores. So here's another example. It's very similar. We're going to look at a tumor reduction problem, and we're going to compare two z-scores. So this is a repeat of the Pressivol and Hypertrova example. In this one, a radiologist is evaluating two patients after they completed different types of radiation therapy. The goal is to determine which patient had the better outcome in terms of tumor size reduction. For a group of patients treated with Radiumex, the average tumor size reduction is 20 mm, and the standard deviation is 6 mm. Okay, so we have a mean and we have a standard deviation. And you know what? Actually, I should start using X bar and S because these are trials. So we're going to use X bar and S for the mean and standard deviation. Okay, so X bar and S. Now for the other group, they were treated with a medication Radiovant, and the average tumor size, X bar, was 15, and the standard deviation was 3. Patient 2 experienced a tumor size reduction of 19 millimeters. So we see, comparing the two patients, patient 2 reduced by 19 millimeters, patient 1 reduced by 22 millimeters, and now we're going to compare z-scores. Calculate the z-scores for both patients. We're going to round to 2 decimal places and decide which patient had the better tumor reduction relative to its own distribution. So the important thing here is not to just say which reduction is more, because it's easy to see here that this 22 is the bigger reduction. That's not the question. The question is saying which patient had the better tumor reduction relative to its own distribution. And the answer to that question is a z-score. Which z-score is better? So comparing two z-scores, let's compare z-score for patient 1. We have an average of 20, that is the mean, and a standard deviation of 6. Patient 1, the X value is 22. Okay, and that's not the right unit. It's just 22 mm. Let's find the z-score for this person. So we have x minus the mean divided by the standard deviation. Let's take 22, our x value, minus the mean 20, and divide by a standard deviation of 6. So when we do this, we're going to get 0.333 repeating, and we have to round to 2 decimal places, so we're going to round that to 0.33. The z-score for patient 1 is 0.33. So let's interpret what that means. Their tumor size, the z-score for patient 1 was 0.33. Their tumor size reduction is 0.33 standard deviations above the mean. This indicates a slightly better than average outcome with RadioMax. So we've got an improvement, and it's slightly better than average. Let's take a look at the next patient with the other medication. Okay, Radiovant. The average is 15, and the standard deviation is 3, and patient 2 improved by, and that's not the right units, it's just millimeters, 19. So let's find the z-score for a data value of 19. So we're going to take 19 minus 15 divided by 3. X is 19, mean is 15, and 3 is the standard deviation. So we do this, and we are going to get a number that's better than the last z-score. 1.33 is our z-score now. And to interpret that, we're going to say the z-score for patient 2 is 1.33. Their tumor size reduction is 1.3 standard deviations above the mean, and it suggests a significantly better than average outcome with this other drug. Okay, so let's take a look now at the comparison between the two. One of those patients had an improvement that was 0.33 standard deviations above the mean, and the other one had an improvement that was 1.33 standard deviations above the mean. So which patient had the better tumor reduction relative to its own distribution? Patient 1 with RadioMax or patient 2 with Radiovant? Now remember, patient 1, 0.33, and Radiovant, patient 2, 1.33. And the answer is patient 2 because of the larger z-score. Patient 2 has the better tumor reduction relative to its distribution. Patient 2 had the higher z-score of 1.33, indicating a better outcome relative to the patients in their group. Okay, so we can't always look at the values of the tumor reduction to answer these questions. It's not necessarily a question of which tumor was reduced more, but rather which patient had the better reduction relative to their group. And that is always a measure of z-score. Okay, so even though patient 2 had the lower tumor size reduction, their outcome stands out more relative to others in their group. And we could see that when we graph the two. We graph 1.33 1.33 up here compared to 0.33 down here. Okay, so that's the z-score formula, and that's how we apply the z-score formula and do comparisons. If we want to reverse the idea, and instead of finding the z-score, if we want to find a data value given a z-score, we can use this other formula called the raw score formula. It's the same as the z-score formula, but it's solved for x. So this is the formula for a z-score. Z equals the data value minus the mean divided by the standard deviation. If we use some algebra, we could rearrange the formula so the x part is on the left, solving for the x. So let's take, we can either use the sample and the sample mean and the sample standard deviation, or the population mean and the population standard deviation. And we would solve for x. Okay, put x by itself, isolate x, and we get x equals z times s plus x bar for the sample, or x equals z times sigma plus mu. In this form, we call this the raw score formula. Instead of finding a z-score, we're finding the data value or the raw score. So let's apply this raw score formula to solve some problems. So we're going to make sure that we remember this score, this formula, or this formula. It works the same way whether or not you're dealing with a population or a sample. It's just the symbols are different. So let's go back to forced vital capacity. A respiratory therapist is evaluating a patient's forced vital capacity, the maximum amount of air a person can exhale after a deep breath, and the therapist knows that the forced vital capacity average for a group of similar patients is 3.5 liters. Okay, so let's say that's the average, X bar. And the standard deviation is 0.5 liters. So we're looking at a different set of people than we were in the previous few problems on FVC. So we have a different mean and a different standard deviation in this case. In this group, there's a patient with a z-score of, there's a patient with a z-score of 1.4. Okay, so it means that their FVC is 1.4 standard deviations above the mean. Now, we know visually what that looks like because the mean is the center, and 1, 2, 3 standard deviations above makes 1.4, maybe around right there. But this question is asking us to take that a step further and take that 1.4 z-score and convert it into an actual forced vital capacity value. What is the person's raw score? What is their FVC score? Or their FVC measurement in this case. Okay, so let's use that formula that I just provided and plug in the mean, the standard deviation, and we were told the z-score 1.4. And let's see what we get for the forced vital capacity. Okay, so again, we have the mean, we have the standard deviation, we're provided a z-score for this particular patient. Now let's calculate the raw score. So let's start with the actual raw score formula. X equals z times s plus x bar. We're going to plug in what we know. We know z, s, and x bar. So let's plug those values in. 1.4 is z times 0.5 is s plus X bar is 3.5. So let me take you to the the calculator, and show you this calculation. So showing you this calculation, we're going to apply it. We don't need parentheses. 1.4 times 0.5 plus 3.5. Okay, no need for parentheses because the order of operations will take care of this in the right order anyway. We're going to take the z-score 1.4, multiply the standard deviation 0.5, and then add the mean 3.5. So this gives us a forced vital capacity of 4.2. Okay, forced vital capacity, the raw score is 4.2. Okay, so our answer is 4.2 liters, and let's interpret what that means. The patient's actual forced vital capacity is 4.2 liters. This is 1.4 standard deviations above the mean of 3.5. Now, how do we know that? Because we were provided with a z-score of 1.4. And we know that when we calculate the raw score, we get 4.2. So a z-score is a measure of how many standard deviations away from the mean a value is, and 1.4 is positive. So it follows that 4.2, the forced vital capacity for this patient is above 4.2 is above the mean of 3.5. It indicates better than average lung capacity. Okay, let's try another example. For a group of patients, the average forced vital capacity is 3 liters and the standard deviation is 0.6 liters. So we're going to change mu or change X bar here to 3 and change S to 0.6. A patient in this group has an FVC z-score of negative 0.5. So we're going to use a z of negative 0.5. Now we know with a negative z-score that this person's forced vital capacity must be less than the mean of 3. But let's find out exactly what it is. It's going to be less than 3, but let's see exactly what it is. So let's, after we calculate it, we're going to interpret the meaning of the patient's, I should say here, the patient's forced vital capacity. I'm sorry, no, first we are going to measure, oh, I'm sorry, we are going to talk about the interpretation of the z-score. So let's do that first. After we interpret the z-score, then we will calculate the raw score and we can interpret that. So a z-score of negative 0.5, sorry, a z-score of negative 0.5 means that the patient's forced vital capacity is 0.5 standard deviations below the mean. So I did say that before, but let's write it out so we really understand this. The patient's forced vital capacity is 0.5 standard deviations below the mean. Now we know that because negative z-scores are below the mean, and a z-score is a measure of standard deviations away from the mean. So 0.5 means half a standard deviation below the mean in this case. Okay, so that's the patient's FVC value. We know because we know the patient's z-score. Now let's calculate the patient's raw score. We use the raw score formula, x equals z times s plus x bar. And let's plug in z is negative 0.5, s is 0.6, and x bar is 3.0. And plugging that in, we get 2.7. And let me just take you to the calculator and show you, make sure you understand how to get that. Okay, so we take negative 0.5. I want to make sure you understand where the negative key is. The minus sign is different than the negative key. Minus is above plus, but negative is to the left of enter. That's the one you're going to use here. Negative 0.5. And then you multiply that by 0.6 and you add 3. Okay. So this gives us a forced vital capacity raw score of 2.7 liters. Okay, so forced vital capacity raw score of 2.7 liters. And now we can say that the patient's actual forced vital capacity is 2.7 liters. So we started with the patient's Z-score and we calculated the patient's raw score. So sometimes you have to really be careful on understanding whether or not you're going to use a Z-score formula or the raw score formula in a problem. Let's remember that the Z-score formula, the Z is X minus X bar, the mean, divided by the standard deviation. And in the raw score formula, we have X, the raw score, equals the Z-score multiplied by the standard deviation plus the mean. Now, a problem involving Z-scores could ask you for one or the other. And it's careful reading that's going to guide you into which equation to use, which formula to use. If the question asks you to find the Z-score, you use the Z-score formula. If the question asks you to find the value or raw score, or if it's dealing with forced vital capacity, it'll say find the forced vital capacity value, find the cholesterol value, find the blood pressure value. Those are examples where you're going to apply the raw score formula. Okay, so some key takeaways here. Analyzing data with z-scores allows us to show how a variable's value compares to a distribution's average. So z-scores that are high, like close to number 3, these are far away from average, where the average is 0 for a z-score. A z-score represents the average of the distribution. A z-score of 0 represents the average of the distribution. A z-score of 3 would be far away from that average. And a z-score of -3 would be far away on the other side. So a z-score for a forced vital capacity value shows how a patient's lung capacities compare to the average. A z-score for blood pressure would show how a patient's blood pressure compares to average. So different variables, lung capacities, blood pressure, will have z-score calculations of their own, but in all cases, the z-score comes out to be something roughly between -3 and +3, and rarely going outside of that range. Okay, mostly from -3 to +3. Outside of that range, we have the outliers, and that happens in 0.3% of the time. Okay. So that's the introduction to z-scores. Most students find this a little challenging at first, so it's okay if you have to watch this more than once and practice the problems more than once. But hopefully, after a couple of viewings and completing the homework, you understand z-scores and understand how to calculate and interpret them, and you'll do well on future questions. So I hope that this helps you. Contact me if you have any questions, and I'll see you at the next lecture.